Swayam Prabha. Digital India. Educated India.
Hi friends, now we will discuss on the topic syngas to liquid fuel production. So, in the previous class we have discussed how the syngas can be produced from the natural gas, and now we are going to discuss how this syngas will be converted to liquid fuels. So, the contents of this class is why syngas to liquid fuel, and then some important routes for liquid fuel production from syngas. So, why syngas to liquid fuel? Already we have discussed that if we convert syngas to liquid fuel, then we will be getting more market, we will be getting the value added products, different types of chemicals or some liquid fuels. So, that is the major features of this liquid fuel conversion. Now, we see natural gas which is available in nature. So, from this reserve it can go through the pipeline and then it can be used in different application, particularly for heat application, say it go to conventional market, or it can be liquefied. So, liquefied natural gas, then also we have some supply chain arrangement already existing, and then it will be going to conventional market. So, these are the two conventional routes, but if we go through this third one route, that is GTL route, then this is a new technology, and here we get some large existing transferred fuels market, we have good market and we can get chemicals also. So, that is the advantage, and that is why people are trying to convert it into liquid fuels. Another is natural gas has low energy density, but if it is converted to liquid fuels, energy density will be increased. So, application of this in transport fuel will be easier than the natural gas. Now, we will see different methods which are used for this syngas to liquid fuel conversion. So, one is Fischer-Tropsch synthesis. So, Fischer-Tropsch synthesis, syngas is converted to liquid fuels, that is called say diesel, petrol, kerosene, etc. So, what happens in this case? At first we get wax, then wax is hydrotreated to get different products of it after fractionation. So, the basic reactions we can see here, CO plus H2 we have in the syngas. So, that will produce the hydrocarbon chain as mentioned here CH2N. So, this hydrocarbon chain we can get, or NCO plus 2N plus 1 H2, this reaction can take place Cn plus H2N plus 2 plus NH2O. So, we are getting paraffin type of compounds. Again same other reaction can take place, NCO plus 2NH2, so Cn H2N plus NH2O, olefin type of compounds we may get, and again CO plus H2O, CO2 plus H2, water gas ship reaction can also take place. So, overall reactions is strongly exothermic, minus 180 kilojoule per mole in these reactions. So, we are getting basically hydrocarbons, all paraffins and olefins basics. So, once the paraffins are produced and carbon number is, if this N number is higher, then we will be getting wax. So, that wax is the major product by this first step of this FT synthesis, then that will be converted to different liquid. So, if we see the flow sheet, then we are having the syngas, so 2:1 hydrogen is to CO ratio, then it is coming to FT reactor, then FT reactor will basically give us olefins and paraffins type of compounds. So, higher carbon paraffins means wax. So, we will be having wax here, or we may get some oil, light oil and light wax we will also get. So, it will be gas phase, it is coming here. So, it is going out as a vapor and then it is coming some gas and vapor. So, gas is recycled and the condensed part is coming out, that is we are talking about light oil and light wax, and this is wax from the bottom of the reactor we are getting. So, this light wax and heavy wax, these two wax will be hydrocracked here. So, after hydrocracking there will be the conversions of the high molecular weight paraffins to low molecular weight paraffins, and then we will get the distillation and we will get different fractions. So, we will get off gas, that can be combustions as flare, and then naphtha, we can get kerosene, we can get distillate, diesel, FT fuel, other FT products. So, that way we can get the liquid fuels from the natural gas. Now, these reactions, at what part we are taking the reactions and what type of catalyst we can use, that will influence the distributions of these different products, and that part we will go to discuss now. So, here we see the process conditions and catalyst. So, H2 by CO ratio is 2 to 2.2 and then pressure is 15 to 30 bar, and temperature, as we mentioned, there are two temperature range has been reported, that is 325 to 370 degree centigrade high temperature and low temperature 220 to 270 degree centigrade. Obviously, we will see the variations in the product quality by the application of different temperature range, and GHSV, gas hourly space velocity, is 700 per hour, and the catalyst basically has been used is iron based, cobalt based and ZSM pipe supported bimetallic FT catalyst for gasoline synthesis. So, this Fe based iron based catalyst are fuel flexible, but CO based catalyst suitable for high hydrogen by CO ratio and preferable for natural gas based syngas. So, we are talking about natural gas. So, CO will be preferred for this case, and as you mentioned, we have two temperature range, one is 3 to 350 and another is 220 to 270 degree centigrade, and under these two different operations we will see the distributions of the product. So, here high temperature range means 330 to 300 to 350 degree centigrade, we are getting C5 plus is equal to 50 to 80%, and here we are getting C5 plus 20 to 30%. So, low wax we are getting high temperature, low percentage of low wax, lower percentage of low wax, and here we are getting 50% of wax. So, wax we are getting higher when the temperature is less, and gasoline to diesel ratio, at high temperature we are getting more gasoline, at low temperature we are getting more diesel, and high temperature we are getting Cetane number 50 to 60, low temperature we are getting Cetane number 80. So, at lower temperature we are getting diesel, more diesel with more Cetane number. So, depending upon the need in the market, we can choose what type of FT synthesis reaction we will prefer at low temperature or high temperature. Now, we will show some commercial plant available in the world for this liquid fuel production from the natural gas. So, one is Australia here, then Qatar and Italy and South Africa and then Malaysia. So, here some plants are already available on the base of natural gas, and these are the capacity. So, we see here these are very big capacity also, and they have used proprietary catalyst and some iron based and proprietary catalyst not shown here, but the technology licensors are Shell and Accents with NE and ISP, and gas LTM technology is also used some cases. So, these are the technology licensors, and we also see that the plants are not very old, it is started in 90s and 2006 one like this. Now, we are coming to methanol synthesis. So, methanol can be produced from syngas. So, how we will do it? So, this is our biomass waste to syngas, but in our case this is methane reforming, then it will give us syngas. So, then that syngas which we are getting, that will be converted to methanol. So, what is the condition? We need one catalyst that is copper based catalyst has been used widely, and copper, zinc oxide, alumina, and then H2:CO ratio 2:1, and this is the reactions. So, that way we can produce methanol. Overall reactions very simple way I have mentioned here, but this is not very simple because it is gas and solid phase reaction. So, I will discuss more. Then for this conversion, two technology licensors are capturing the market basically. So, one is your ICI technology, another is your Lurgi technology. So, this ICI process was first commercialized in 1970 and currently accounts for more than 70% of undergoing projects. So, this ICI process is having more application. Now, we will see what are the reactions which take place during this methanol synthesis. So, obviously, we have syngas. So, CO and H2 we have, it is giving CH3OH, and we need some carbon dioxide for the initiation of the methanol reactions, and so that CO2 H2 CO plus H2, and it is believed that CO is first converted to CO2 and then CO2 reacts with CO and H2 and then it gives methanol. So, this CO2 plus this H2, this is the major reactions for methanol synthesis. So, for these different reactions we have different delage value as mentioned here, somewhere we are getting exothermic, somewhere we are getting endothermic. So, the one important conditions or pre-requirement to get required conversion of syngas to methanol, the R value, that is I discussed that H2:CO ratio, that is around equal to 2, it is used for this application, but here later the another factor has been developed because of this complex reaction scenario, that is what is R is equal to, it is given here H2 minus CO2 divided by CO plus CO2. So, this what is the concentration of these 4 gases, these 3 gases, that will give the R value as with this expression. So, R value is basically around 2, when we maintain it at around 2 we get suitable conversions of the syngas to methanol, and as it is a solid gas phase reaction in the conventional reactors. So, one pass conversions of CO is around 25%. So, that is why we need a very big reactor for the conversion of syngas to methanol, and the process operates at 220 to 250 degree centigrade and 5 to 8 megapascal pressure and uses a series of catalytic adiabatic reactor beds. So, this is the features of the important features of the methanol synthesis reactions. So, apart from those major reactions, here some other reactions takes place. As you see here, methanol is converted to CH3O CH3 dimethyl ether, and then dimethyl ether to hydrocarbons and plus H2O, and this methanol plus CO plus 2H2O, that can also give us CH3 CH2OH. So, what we are getting, some side reactions are going on in this reactor that produces hydrocarbons, higher alcohols, even some amount of ether. So, these are the other reactions which can take place. So, we can get say syngas R value around 2. So, methanol reactors we can get the unconverted syngas recycling and then methanol purifications. So, this is the concept of methanol production, and the catalyst basically copper and zinc oxide based catalyst, and other catalysts have been used chromium zinc oxide, zirconium potassium, zirconium manganese potassium, and zirconium zinc oxide and high pressure 240 to 300 bar. So, this is not that efficient one because high pressure and high temperature is required. So, once we get the methanol, so that can be used as a building block for different types of chemicals. Some of the chemicals which we can get as mentioned here, we can get dimethyl ether, we can get ethylene, we can get propylene, we can get polyolefins, we can get oxo chemicals, methyl acetate, acetic anhydride, acetic acid, acetate ester, ketene, diketene, etc., and many more. So, conventionally methanol is produced in a gas solid phase reactor and heterogeneous catalysts are used, and we have already seen that 25% conversion is possible, and the catalyst requires high purity of the syngas. If small amount of sulfur is present, then the catalyst life reduces and it harms the whole process. So, to eliminate those limitations, the low temperature, low pressure methanol synthesis methods are being developed, and in this case we use some homogeneous phase reactions and then homogeneous catalysts are used. Some examples is Brookhaven National Laboratory BNL method. So, they have a homogeneous nickel catalyst and alkoxide in an organic solvent, that is trimethylene glycol dimethyl ether triglycerin. So, this organic solvent is used where nickel catalyst and alkoxides are mixed. Then in this liquid phase syngas is passed through it and reaction takes place. Another is methyl formate formation method. So, this employs a mixture of copper based oxide and alkoxide as a catalyst. So, one is nickel based catalyst, another is copper based catalyst, and then alkoxide and this triglycerin media solvent the people have used and studied the conversion of syngas to methanol. And basic reactions has been reported as CH3OH plus CO, HCOOCH3 particularly for methyl formate process. So, I am getting methyl formate and then methyl formate is further converted to methanol. Okay. So, both these processes we see here, this requires around 100 degree centigrade and it requires 20 to 25 bar, unlike say 60 to 80 or 90 bar or somewhere 200 bar, we are getting here by 20 to 25 bar, and temperature is also less 100 degree centigrade. So, now it has been reported that if we can use some nanocatalyst based nanomaterial based catalyst, then this performance can be further increased, but this is under development stage and not in commercial scale. Now, we will see how we will select the reactor type, what will be the type of reactor for the methanol synthesis. So, this is the thumb rule we can say, that is the reactor selections for methanol synthesis. We have given here, say we have liquid reactions may take place and liquid solid reaction may take place, liquid gas solid reaction may take place, gas liquid solid reaction can take place. So, different types of phases may be available during the reactor, and depending upon that we can select a particular type of reactor for that to perform that specific reaction. In our case we have syngas, that is CO plus H2 in gas phase and then solid catalyst. So, we need gas and solid. So, this is our domain we have to choose. So, for these applications we get multi-bed reactor, multi-tubular reactor, fluidized bed reactors and monolithic reactor. So, these reactors are more suitable for the conversions of syngas to methanol. As we have discussed, there is a multi-tubular reactor is commercially used, tubular reactor is used commercially in most of the technology available in market, and we see the typical plant operation, the catalyst lifetime is about 2 years, but if sulfur is present then it reduces. So, sulfur condition, sulfur in the syngas should be less than 0.5 ppm, 0.5 ppm. Catalyst deactivation also occurs due to thermal sintering of catalyst. Above 300 degree centigrade copper oxide starts to crystallize, which reduces the activity of catalyst. And then plant economy is a function of operating temperature, pressure and recycle ratio, and as you have discussed, the carbon dioxide is required for these reactions, and 5 to 8% of carbon dioxide in syngas feed is required to initiate the methanol synthesis reactions, and temperature of the reactor is controlled by controlling steam pressure through cell side. And we see the reaction mechanism. So, overall reactions, although we have CO plus H2O, it is giving up CO2 plus H2 and then CH3OH. So, carbon monoxide is converted to CO2 and then it is giving us methanol. This is the overall reaction, but how it happens, this is not very so simple. Then Froment proposed a redox type of mechanism. So, here carbon dioxide. So, what happens in this case? So, you are using your syngas and it is going through the catalyst bed. So, diffusion of the gas molecules through the pores is the first step, then active sites are there in the catalyst. So, reactions at the active site takes place. So, now on carbon dioxide it is coming with this active site, say solid S plus. So, that is it is giving us O2 plus OS solid and then CO, or it can also give this OS, one OS and another S. Carbon dioxide can also mix with this and gives us CO3 2S, two sides combinedly it gives CO3 dot 2S. Then CO3 2S, some Hs may combine and give this one. Further this can combine with another S and then it can give this one. So, that way different types of products, intermediate products are formed, and here also we can get OS which we are getting that can react with Hs, another site containing hydrogen. So, that can give us this one. Similarly, this one. So, this ultimately we are getting H2O, we are ultimately getting CH3OH, and here hydrogen is added, CO2 and hydrogen, that we are talking about CO2 and hydrogen. So, this hydrogen is converted to 2 Hs. So, this is the source for Hs and this is the source of Hs. So, this is the scheme through which the methanol and water is formed. This is proposed by Froment and they have modeled the reaction. Now, coming to DME synthesis. So, DME synthesis we can get here, as we have seen that methanol to DME just dehydration reaction is required. So, we can get the methanol first from the syngas, then dehydration we will be using some special catalyst, and after dehydration we will get the DME, or direct from syngas to DME is also possible using another type of catalyst, bifunctional catalyst we can do it. But here basics will be, we are having here biomass waste it is shown, but we can use methane also. Then gasifications will be replaced by reforming and then we will get syngas, and this will be the reactions. Already we have discussed this one, and this is methanol is dehydrations and DME, or this is the direct route also. But here we see H2CO requirement is 1:1, but here we need 2:1 for methanol, then further dehydration. So, this is the difference between the H2/CO requirement for these two routes, and this is your flow sheet. Say natural gas, it will go through reformer. So, if it is steam reforming, then we can get more hydrogen, hydrogen can be separated, and 1:1 H2/CO requirement for direct method and 2:1 for methanol synthesis route. So, that is 2 to 2.5 is maintained here, rest hydrogen is recovered, and then it is going to methanol, then methanol unconverted syngas, then it is dehydrated, and for dehydration it is going to DME reactor, and after dehydration we will get DME, DME will be separated, and again if unconverted methanol, that will be recycled back here for the further DME conversion, and here we will be getting the water. So, this is the flow sheet through which the DME can be produced from the natural gas. So, DME synthesis we see reactions and catalyst. So, using dehydration catalyst like alumina along with copper, zinc and alumina based catalyst, we can get DME from the methanol, and if we get DME, then it has low ignition temperature, very high cetane number and high oxygen content, very low particulate emissions. That is the advantage of DME, and it is suitable as source of hydrogen for fuel cells. It can also be used as additive to biofuels to improve their ignition characteristics, LPG substitute and diesel engine. It has versatile application, and then these are the technology licensors for DME, that is Chevron, Haldor Topsoe, Total, NKK, Mitsui, etc. Now, we will see some example of DME plants. So, China's is the leader of DME synthesis, and China's current annual output of DME is 1,20,000 tons, and it plans to produce 20 million tons of DME based on coal feedstocks by 2020, and already on the roll is 2 lakh tons coal to DME plant at Shanghai. So, coal to syngas and like this. So, natural gas can also be processed like this to syngas, natural gas to syngas, and that syngas to DME. And other countries which are taking strides in setting up DME plants are Japan, Iran, Russia and Qatar. And there are some issues with syngas utilization from stranded natural gas. So, natural gas may be available in some remote area in less amount. In that case, the technology should be different. So, small scale reactor are basically needed for that application, and it has been reported that the gas to liquid conversion processes can be economically feasible when the plant capacity is very high, that is 30,000 barrels per day or more, but these stranded natural gases will be having less reserve and it is in remote area. So, we need to convert it at lesser amount. So, that is why it is it requires some development in the reactor side. So, small scale plants for fuel production from syngas is required, and recently smaller scale GTL plants are designed to be economic at 1500 barrel per day to 15,000 barrel per day. So, initially it was reported 30,000 barrel per day will be economic, but due to the development in the reactor side, now it is possible to 1500 barrel per day to 15,000 barrel per day. The Veloci's have reported it, and then the Veloci's first commercial plant is now under constructions in this. The plant is jointly venture between Veloci's Waste Management. Another plant in planning stage is Ashtabula, Ohio near Lake Erie, using natural gas from the Marcellus shale. So, initial productions will be 2800 barrel per day. And then Oberon Fuel, they has developed small scale methanol plant which can utilize syngas from natural gas as well as biogas containing 50% of carbon dioxide, and typical capacity of the plant using syngas derived from natural gas as well as biogas is 10,000 gallons per day DME or 11,300 gallons per day methanol, and footprint of the plant is 40,000 square feet, and feedstock required is 12 lakhs 40,000 standard cubic feet natural gas per day, 15 lakhs 40,000 standard cubic feet biogas per day. So, we have discussed on the processes how to convert liquid fuel from the syngas which can be derived from the natural gas. So, up to this in this class. Thank you very much for your patience.